Question 2. Sketch the region whose area is given by the integral below and evaluate the integral. So first off, I wrote out what my region R is. This is the region. I will provide two sketches for you. Sketch number 1. We first notice a cosine of theta over 3 has period 6 pi. Because cosine theta has period 2 pi, now we're taking 3 times as long to complete a period. So if I had to graph this, one way to graph it is like this. So let's say this is 1, or not 1, that's 6 pi. Divide that by 2, divide this by 2, divide that by 2. Okay. So this is 3 pi over 2, this is 3 pi, this is 6 pi over 2, and then this is 6 pi. Sorry, not 6 pi over 2, that's 9 pi over 2. Okay. And then, if I were to graph this, let's say this is radius 1, r equals to 1. If I were to graph it, the graph of cosine looks like this. And please excuse my very bad drawing. So that's supposed to be the graph of cosine. Let me give that another shot. Okay, so that's supposed to be the graph of cosine. But we know that our theta values, they only go from 0 to pi over 3. So our region R is really just this shaded area here. It's nothing more. That's sketch number 1. Sketch number 2. So we observe if theta is equal to 0, then cosine of theta over 3, that's just 1. And if theta is equal to 3 pi over 2, then cosine of this, that's just pi over 2. Cosine of pi over 2, that's 0. So if I were to then put the Cartesian xy and graph it with a polar mindset. So when the angle is 0, the radius is 1. Let's say this is radius 1 out here. I will start out here. And as you see, as the angle gets larger and larger, the radius gets smaller and smaller, as you can see in that. So eventually, as I continue increasing the angle, I get closer and closer to the origin. So this is what it will look like. So first extend that. Okay. And it's getting closer and closer and closer to the origin. Something like that. And then it hits the origin when it's at 3 pi over 2. Okay. So now let's find the area of this shape, of this shape specifically. And the way to do that would be to use polar coordinates. It's a lot easier. So the area is equal to double integral 1 dy dx over the region R, but instead of using xy's, let's use polar. So you have an adjustment factor of R, dr d theta, and we know the R values go from 0 to cosine theta over 3, and then the theta values. And the theta values go from 0 to 3 pi over 2. So let's integrate this. Okay, so that's what, 1/2 r squared, and r values are going from 0 d theta. Simplify that. So cos square theta over 3. And the next part's radius is 0, so it's just 0. Right? 0 squared and 1/2 of it. And then we recall the double angle formulas, and we have this. So in the context of x equals to theta over 3, what we now have is 1/2 times 1 plus cosine 2 theta over 3 over 2 d theta. But now all the hard work is done. It's just an integral of one variable. Just simplify it first. So you pull out 1/4, that becomes 1 plus cosine 2 theta over 3 d theta. And the rest is just first year calculus now at this point. So that's equal to 1/4. This will be theta, what's this one? 3 over 2 sine 2 theta over 3. And the theta values go from 0 to 3 pi over 2. So that's 1/4 3 pi over 2 plus 3, and then sine pi minus sine 0. So sine pi is 0, sine 0 is 0. And if you keep simplifying that, you get 3 pi over 8. And that's the final answer.